Aloha, and welcome to this session of Shadow the Scientist. My name is Jamika Marshall, and I'm pleased to serve as the coordinator of the STS initiative. In this session, we are very pleased to be shadowing the C3VO team, hunting giants at the edge of the universe. We join the team already set up in progress, and we have 5 members of our observing team here, led by Dr. Brian Lemaux. Brian, good morning.
Good morning, Jamika. How's it going?
It's going good. It's going good. I'm really excited because I think, as you were saying, that the weather is actually good and you all are on sky observing.
That's right. Yeah. So we're observing so I'm observing from Hilo, Big Island of Hawaii. But we're observing on the summit of Mauna Kea with Keck 1. And the summit of Mauna Kea has been fairly cloudy and humid for the past 4 or 5 nights. And even for the first half of this night, it was very cloudy. But luckily, there's been a break in the clouds and no humidity, so we are on sky and we're observing exactly what we want to be observing, which is a miracle.
Well, we are excited to be along
So I
for the
can
ride.
share. See here. So I'll just share what we're looking at now. I think they just refreshed. So this is the these are the cloud cameras from the Keck Observatory. And you can see over here that they have 4 cardinal directions. They have about 120 degrees field of view for each one of the cameras. And they refresh every once in a while. That's why you're seeing them kind of flash off. But let's see, is this right now? This is a little bit earlier. Oh, no, I'm unstable. Can you guys hear me?
Yes, I can hear you.
Okay, good. So if you can see these pictures, this is basically what we're looking at now. It's a little bit earlier in the night, but very few clouds up in the sky, and we're pointing. So we're using this telescope here, and we're pointing up towards zenith, close to the top, about 90 degrees up. So not a whole lot of clouds there, which is great. Exactly what we want. So
Fantastic.
yeah, so we're using an instrument called MOSFIRE this evening, which is a near-infrared spectrograph, multi-optic spectrograph, and the idea is to observe a large number of galaxies. So this instrument allows us to collect light from up to, I think it's 42 galaxies at a time in theory. Although in practice, usually we do about 20 to 30 or so. And so we collect their light, it's put through a dispersive element, and then we get the spectrum of each one of these galaxies. And so we usually do this for quite some time. So usually our total observation of 20, 30 galaxies at a time is roughly an hour and a half. And so we're right in the middle of doing that right now. So we're on what's called slip mask, and we're observing somewhere in the neighborhood of 25 galaxies in a suspected overdensity of galaxies at the edge of close to the edge of the universe. Complete. So about 1.5 billion years after the Big Bang. And so you just heard an exposure complete. We're taking this is in the near infrared. So in the near infrared, the sky is very bright, like blindingly bright, and it's very variable. So both the relative and absolute sky emission changes on a fairly rapid time scale. And so we observe just about 2 or 3 minutes at a time. So you'll hear that exposure complete every 2 or 3 minutes. I think in this case it's 3 minutes. And then we move the telescope just a tiny little bit, and then we observe again, and we're basically doing difference imaging. So we're doing a first exposure minus a second exposure. We're removing the sky background, and then trying to have our galaxies pop out by contrast. So we have a big observing team here tonight. In fact, most of the STS guests. Uh, so if we could just maybe, since I guess we're in a kind of quiet moment right now, I don't know. So maybe I'll go to Ben first, because Ben is driving the telescope tonight. So Ben can give us an update as to what we're doing right now, and if we're going to be moving, making any big moves anytime soon.
Yeah, so hi everyone. I guess I can only see a couple people on, but yeah, I'm Ben. I'm C3VO team here. Just real quick to Brian's question. Yes, we still have some time until we're going to our next target. So yeah, we can chat about things for a bit here. Yeah, so this as Brian mentioned, this kind of region of sky that we're targeting has an overdense region of galaxies, what we sometimes call a protocluster of galaxies. Which is, we believe, the progenitor of one of the massive clusters of galaxies that we see in our local universe, like the Virgo or Coma clusters. And so the main goal of this observing run is to confirm some of the member galaxies in that structure. I think from our previous observing runs, we have over 100 confirmed so far. And we're hoping to maybe get up to 150 or 200, depending on how our data taking goes. As Brian said, we've had some nights that have not been conducive to getting good data, but fortunately tonight is not one of those. And so yeah, so we have, as Brian said, a bunch of different masks that have been designed to target various candidate members of the structure. And the masks are designed using a whole bunch of data that's already been taken on these galaxies, mostly imaging and different band passes or wavelengths of light. And from modeling the different patterns that we see in those combinations of images, we can pick out the candidates which we think are most likely to be members of this structure. And so that's what we're doing. And I feel confident I can say we'll be able to share some of our results from earlier tonight in a little bit. So looking forward to seeing what we've gotten. It'll be exciting.
How much longer do we have on this target, Ben, before we make a move?
Yeah, so I was gonna do, let's see, 4 or 5 more frames, 5 more exposures. So we got 15, 20 minutes.
Okay.
With overheads. Yeah.
Sounds good.
Yeah.
I guess I can share one of the screens. So I'm actually trying to monitor our data at the same time. But let me just share a screen so at least you can see something.
Yeah. And so I think in the chats, sorry, go ahead.
Oh yeah,
no,
that'd be great. Yeah, if you could share, that'd be awesome. If that's what you were offering, sorry.
Yeah. I was gonna give a little bit of background and then move to the observing. So
yeah, that'd be great. Yeah.
Hold on, let me do iPhone start. Okay. Probably is a regular, so we can move a little bit faster, but okay. Is that the right screen? I think it is. Okay, so let's get started. Okay, so you might have already seen this very famous picture that was taken using JWST.
Maybe for Rob's sake, do you want to introduce yourself and
yes.
like say what physical location you're in? Because I think we're all over the world here.
Yeah. So actually that's a good, I have something. So I am a postdoc in this group, and all of us kind of study galaxy protoclusters in the early universe. and we study different aspects of that. So I will be talking some of those aspects. And Ben Forrest is also another postdoc in this group, and Priti Staab is a graduate student. I'm sure they will be happy to introduce themselves. And Emmett is also part of our group. So actually, if I show the globe right now, so the yeah, so the telescope is here. I am here near San Francisco. Ben is here on East Coast, and yeah, sometimes we have participants from all over the world. So we are like around 90 degrees from the telescope right now.
And I guess
Yeah.
Emmett's in Beijing, and then
That's
Priti's
true.
in Oklahoma or
Oklahoma.
Texas, right?
Oh
Yeah.
my God.
Yeah,
So somewhere
we're
in the
Taking
middle
over the
all over the
world.
place.
between you and Ben.
Global endeavor.
Yeah. So we are truly a global team. Okay. So as I said, we study galaxy protoclusters, which are galaxy clusters that are in formation in the early universe. And because I stopped the slideshow, it actually got stopped. So let me start it again. Okay. So you might have already seen this picture of galaxy clusters. Now, how do this? So these are galaxy clusters are basically, systems where sometimes hundreds or even thousands of galaxies are collected, and these are like very gravitationally bound systems, and they are one of the most massive structures in our universe. So large structure that has hundreds or thousands of galaxies, they are gravitationally bound, and this kind of dense environment, sorry for the train, dense environment can affect lots of properties of galaxies. So, but how are these structures formed? So if we look at some of the simulations, I don't know if you can hear the sound, it's a bit so here is a simulation of formation of galaxy clusters. You're basically looking at as the universe, okay, the sound is a bit too loud. So as time progresses, you have some denser region of gas that kind of collects more gas and then also ejects gas. So as it progresses more and more, at some point, things can get really crazy, but we will see that eventually you have like galaxies forming, but even galaxies themselves, like the whole system is very dynamic. So due to gravity, you can have like this kind of formation of galaxy clusters, which has lots and lots of galaxies in it. And this can, how the structure looks, can depend on like at which point in the history of the universe you are looking at them. And also you can see like how do you define the boundary of the cluster, right? Like is it just this kind of like clear boundary, or do you also want to include this other stuff? So when you're dealing with observations, there are lots of challenges to actually define the system, and there can be slightly different ways to define like exact boundaries of this kind of structures. So yeah, so mostly they form through gravity, and they can have many different types of galaxies, like varying sizes, varying shapes. And so, as I said, like it very clearly depends on at which point in the history of the universe you're looking at them. So currently, when we look at massive galaxy clusters, they have lots and lots of galaxies, and the galaxies in these structures look very different compared to when you look in the past of the formation of this kind of structures and how the galaxies look in these structures. So when we actually look at the observations of galaxy clusters in the nearby universe, they look kind of like this. So as you can see, there are lots and lots of elliptical galaxies, okay? So kind of like egg-shaped galaxies. And then when you look at the field galaxies, so galaxies that are not part of cluster, they are kind of more spiral galaxies. So to kind of quickly summarize what we see. So I don't have lots of graphs. This is just only one of them, one or two of them. So here we basically have, as you go from field galaxies, so galaxies that are in less dense environments to galaxies that are in dense environments or galaxy clusters, the fraction of spiral galaxies drop. So in other words, there are more fraction of spiral galaxies in field galaxies. And if you look at cluster galaxies, most of them are elliptical or irregular. And these elliptical galaxies in the cluster environment, they don't show a lot of star formation rate, but they are very, very massive. So in fact, most of the massive galaxies, if we look in our local universe, they reside in this kind of cluster environment, okay? So then the question is that because these massive galaxies aren't forming a lot of stars right now, they must have formed their stars sometime in the past through very rapid growth. It's kind of like if you look at people living in cities, and if they have lots and lots of money, but if they are not earning much money right now, then you must be wondering, like, how did they make all this money, right? They must have done something in the past or have, acquired all this wealth through some mechanism in the past. So it's kind of like that. So these galaxy clusters are kind of like cities of galaxies. And what we are trying to do is kind of look in the history of this clusters and trying to understand how they formed and how do this like galaxies in the dense environment build up their large mass, and at what point did they kind of stop forming stars, because as I said, like the galaxies in the local universe, in the clusters of local universe, they don't form a lot of stars. So at what point did they stop forming stars? And then how did the relation of star formation rate and environment density change over time? Because as I showed in the simulations, it can be very dynamic system. So depending on at which point in the history of universe you're looking, this relation can be very different. So there are lots of questions. And furthermore, as these structures themselves are forming and evolving, how did their formation affected the evolution of their galaxies? So there are lots of questions. So that's why we are studying galaxy protoclusters in early universe. So protocluster just means like clusters that are in the process of formation in early universe. At least here we are using that definition. So that was kind of, these questions were motivation for the C3 view survey. So the C3 view survey is the charting cluster construction with Woods and Oral survey. So we, as a part of this survey, we have identified hundreds of galaxy protocluster candidates in 3 different extragalactic fields. And then we kind of follow up them using the instruments on Keck telescope. So we will look more into this kind of instruments in a bit. And so the goal is to better characterize these protoclusters, study them, and kind of also identify like how many spectral members are there, how do they affect galaxy evolution, and some of the questions we already mentioned. So basically, how do we actually find galaxy clusters, especially in the early universe? So the basic mechanism is that so we see this, right? Typically, like you have image of a region of sky, but you, apart from their location, you also have information about their color. And that gives you some information about how far the galaxies are. So if you plot also the color. So if we look at like the 3D distribution of galaxies using this color information, then it would look something like this. So the 3D, this information comes from Redshift. We will look more into this. But so the basic idea is once you have some idea about this 3-dimensional distribution of galaxies, then you are kind of trying to find overdensities of galaxies in this kind of slice of 3D space. So anywhere if you see like very high density of number of galaxies, that's where your structure is going to be. And so an actual method that we use to do that is called Voronoi tessellation mapping. So the basic idea is that you divide the whole region in cells, and each of the size of the cell depends on like how many galaxies are around that region. So for example, if you have like lots of galaxies together, the size of cell is gonna be small, versus if you have galaxies that are far apart, the size of the cell is gonna be bigger. So if we translate that in and kind of show that in colors. So for example, the red color here shows that galaxies are somewhat closer to each other in this region. And then the blue color shows that galaxies are relatively far away from each other. So here, and then if you repeat this process, you can get like this kind of distribution of overdensity metric, or this kind of color metric that shows the number density of galaxies in a given region. Any questions so far? Cool.
This is great. It's fantastic explanation. Please continue. And I
Awesome.
do have a question. I'm gonna drop it in the chat though.
Okay. Wait, do you have a question right now, or?
Yes, I'm gonna drop one in the chat, but I can ask it now. It actually is just going back to the simulation that you showed.
Yeah.
That was actually a really helpful visualization, at least for someone like me who has a hard time visualizing things. It actually really helped. How many data points do you need to create a viable simulation? Because I can imagine that you can input so many parameters. How do you decide exactly what you want to input, and when does it actually become something that you can use to extrapolate meaningful data from?
You know, that's a great question. So I think, so I haven't actually made simulations, but so typically I think with regards to simulations, of course, just like anything else, it kind of depends on what's your question, right? So, but in this kind of simulation where, you know, you are simulating universe in a box, and you have like, you can, because you can see this kind of tiny galaxies here, right? So I think it would be of the order of millions to billions of particles. I can get back to you on that, like what was the exact number used here, but I think it would be of the order of that. Because what they simulate is actually, you start with particles themselves. So you have like dark matter particles and you have gas particles, and then you say, okay, now let me have like, you know, gravitational forces. So each particle has their own gravitational forces, and then so basically what happens is, like, through gravitation, you have certain region, right? Now you cannot continue this like billions of times, because it will be like billions times billions. So then you kind of like do this adaptive measure where it's like, okay, if multiple particles have made this thing, then I'm gonna treat this whole thing as like one thing, and then have another thing, and then so that's also another thing, like depending on what kind of resolution you want, because you can have very high resolution but a relatively smaller number of systems, right? Versus if you want to have not much resolution, then you can have large number of systems. Does that make sense? Because at the end of the day, you're limited by computational power, right? So you have to think it in that way. Like if you really want to study like galaxy mergers or something, then you can simulate like lots of particles in just two galaxies and then have them merged together. So you're going to get a lot of detailed picture, versus if you are dealing with lots and lots of galaxies, then you're going to have like a relatively less number of particles per galaxy, you know? Yeah. Yeah. I will look up like exactly how many particles there are, but I hope that was helpful.
It's brilliant. Thank you.
Can I just add one thing?
Yeah.
So for proto clusters specifically, one of the things that with simulations is that you can't do a small volume, because
Right.
proto clusters themselves are very large, and they're not so common that you need a really large volume when you're simulating a volume of space. You need a really large volume to guarantee that you would actually have one or two proto clusters in your volume. So if you pick a volume of space that is the size of all these sizes are absurdly large anyway, but large enough to fit, you know, the Milky Way in like the you know, some kind of very localized volume. You would never, you know, find, even if you go back far enough in time, you would never find a protocluster because the size that you're looking at isn't large enough. So with protoclusters specifically, there's a lot of simulations that have been done on galaxies that you can't use for protoclusters because you can't look at that overall arcing environment.
Mm-hmm. Good point. Oh, what happened? Yeah. So, so I
So
mentioned
just a little bit to Emmett's point, and these are excellent. That was an excellent question, Jamaica, and it's really like the answer. I mean, we could, I don't know, we could have like 4 or 5 shadow sessions just on that, and I think it would be awesome to have a shadow session with a simulator, to bring somebody in and have them show off their simulations, because I mean that's a huge part of the cycle of astrophysics is that, you know, when I first started studying protoclusters, I used some of the largest simulations, N-body simulations, to help train my intuition. This was a decade ago. So in 2013, people just started looking for these in some of the biggest, well, I guess the biggest simulations at the time. And as Emmett said, that these structures that we're looking at are very rare. And in fact, these like a superstructure like the one that we're looking at this evening, even in the biggest N-body simulations, you only find a very small number of these types of systems. And so it, you know, it's what you see in the simulations may be quite a bit different from what you're actually seeing in real life, not only because I mean, putting aside the fact that the simulations may not be representative of reality, but even if they are, the shape, the size, the mass distribution of these types of systems depends a lot on their dynamical maturity, how old they are, their formation history. And so if you only simulate a couple of these, even in a very large volume, the ones that you may be looking at in real life may be in a different dynamical state, they may be a different age, have different mass distribution. And so that what we call sample variance can play a big role here in kind of in seeing a disparateness between the simulations and the observations. There is a simulator at UC Davis, actually, Andrew Wetzel, who I think would be amazing at this. So we could reach out to him, because he does something called zoom in simulations. So basically, I think as Ekta was saying, you only have a certain number of particles, right? So you can make those particles fairly small, but then you can only simulate a small volume. You can make those particles larger masses or sizes, and then you can do larger sizes. And so I think what Andrew's group does, he works on what is it, a simulation survey called FIRE, something like that. Some cool name. And
it's fine.
they basically take simulations where they identify galaxies of interest that they don't have really the resolution to push the, you know, the I guess what they call subgrid physics, or, you know, basically just getting like detailed information on those galaxies. They have particles that are too large, and so they say, oh, those look like interesting galaxies. What we're going to do is we're going to focus in on those galaxies, and we're going to make the particles smaller, and then we're going to resimulate things.
This exposure, gonna throw a quick dart mark, and then we'll
yeah, so that would be really exciting. And I'll just pause to say that the background noise you're hearing is Ben talking with our telescope operator, and we're actually going to be moving targets here shortly. So this will be, I think, hopefully the most exciting portion of the remainder of the night, at least the most telescope movement. Hopefully.
Yeah.
Maybe we could pause, and then we could watch this, and then we could come back to the presentation, if that's okay for you, Ekta.
Yeah. Do you want to share screen, or I can share screen too?
I think my internet's a bit unstable, so if you don't mind doing that, that'd be awesome.
Yeah.
You can maybe go to, let's see, you could go to tell status screen, so see magic. Oh yeah, perfect, you got it.
Yeah. So basically,
It's like we'll give
sorry.
elevation limit for once, which would be nice.
No, you're good, Ekta.
Okay. So what you're looking at here is, as Ryan said, we are actually moving to a different target, and we will look more into this, like what does this all mean? But right now, we're gonna observe at a different location. So that's why you see this kind of streaks, because it's like when you hold your camera and if you suddenly move your hands, it's kind of like that, like the telescope is moving. That's why you see this kind of streaks. So um, so Ben has highlighted this target, which is where we are going right now. And you can see some of the details here. So this is the location of the target. And this is actually a guider camera. So it's not like we are not using these observations, but this is kind of where you see bright stars. So you know exactly where you're looking at. And this is also used for tracking. So as you know, like overnight, the celestial sphere, like stars kind of move from one side to other side. So if you are continuously looking at some target, it's going to move with time. So you have to make sure that as the star or your system is moving across sky, you want to kind of continuously look at it. So you also have to move the telescope with the same speed. So this kind of helps with that. So that's called tracking. So we'll see in a bit.
Ekta, we're seeing, I think this says OA star list, kind of in the bottom left. Is that the target list for tonight?
Yeah, so this is the overall list, and we are going to this particular target, LZC72. So I'm gonna show in a bit like exactly where that is and how it's relevant to our like broader goal. But that's where we are going at right now. And then apart from that, you also see this screen where you see positions of the telescope and then position of the dome and if the dome is tracking or not, because dome would have slit in it, as you will see, and so you want to make sure that the dome is also tracking, otherwise it will be blocking light. So that has to be taken into account. And apart from that, of course, we have to track these things. So what's the temperature, the humidity, wind, and other things, because they can also affect the observations, but also more importantly, the telescope itself. So if the wind is too high, you don't want to observe, so you have to keep an eye on those things.
I see. Oh, it's still rotating.
See.
So yeah, so right now, so we're you may hear in the background Ben and our observing assistant Julie is moving the telescope, talking. So we're rotating, we're basically rotating the instrument. And so you'll see this rotator mode at the bottom, position angle changing. So we're actually at the location of the target, but we just have to rotate around to get to the correct setup. And then we're going to start configuring our instrument, but we can't configure the instrument as it's rotating around. The gravity vector is changing rapidly, and it can have a pretty serious effect on the configurable units that we have. So basically the mechanisms with inside the instrument. And so we're going to wait until that rotation is complete, and then we're going to configure our instrument. And I think you might be able to show the control 0 screen, Ekta.
Yeah. Yeah, so
Yeah.
let's see.
Yeah, you want to run through this?
Sorry, say that again.
Oh, do you want to run through this, or I can totally run people through it, or as you like?
Yeah, go for it.
Okay. So we're, I think.
Writing will look good for you there.
Sorry, I'm just gonna check something.
Yeah, that looks great. Thanks. Plus 40 and then 72. Yeah, that looks good.
Yeah. Great, so you can send it and then you can start your alignment.
Um, Thanks. I'll go ahead and execute the maps.
Okay.
Probably do the course align actually. I don't know. I think that'll mess up the.
Yeah. Yeah.
Right. So Ben is now configuring our instruments. So this is our instrument desktop graphical user interface. And so this has all of the internal mechanisms, all the mechanisms within what's called the optical path of the instrument. And so we have, if you can see at the top left there, you have the hatch. The hatch is the so is the plate at the interface between the telescope and the instrument. So when the hatch is open, that allows the Keck 1 telescope, which is this giant light bucket, to throw this light to MOSFIRE, which is the instrument. So each one of these telescopes, Keck 1, Keck 2, all the telescopes on Mauna Kea, pretty much all the telescopes in the world have many instruments, and so so the light bucket collects the instrument, collects the light, and then throws that light to the instrument. And this is through this hatch, and then there's the pupil. And then the next thing in the optical path is the filter. Currently, we have it as dark because we're moving various mechanisms with inside the instrument, and we don't want to expose the instrument. It's a very sensitive instrument, so we don't want to expose it to light, unwanted light. So right now, as things move around, we're making sure that the inside, so where the detector is dark. And then the final optical element before the detector is the grating. This is the dispersive element, so this is what creates the spectra. And so down at the bottom left is what's called a configurable slit unit mask. So these are bars, basically, that are in a cryogenic environment, and they move back and forth. And there's, I think, 42 or 43 of these. And they move back and forth to create either boxes or slits at specified locations. So prior to the observation, we use images to determine objects of scientific interest. And then we want to set up a slit on each one of those objects of scientific interest. And so this is what Ben has done. And so we have everything ready at this point. And so we're just moving these configurable slit units into place to create our mask of slits. And then behind this mask of slits is the detector. So the dispersive element, the grating, will disperse the light for each one of these galaxies, or what we think are galaxies. They could be stars, they could be other things, it could be little hot pixels on on the detector somewhere. But we're hoping they're galaxies. We're hoping they're galaxies in this overdensity of galaxies. And then we get a spectrum for each one of these galaxies. And so, Ekta, if you can go to what is that? Control 1. Yeah, perfect. So this is our slit mask. This is what it's supposed to look like. And so each one of these little tiny dots, different colored dots. So the color actually represents something. The color, so the redder colors are our highest priority targets. So these are the galaxies that we think have the most scientific leverage. Yeah, Ekta just pointed out up at the top right is a priority. And so so red all the way to blue, I believe. Blue is the lowest priority. So you can see that number changes by a factor of 4 or so. And so we determine based off of the brightness, based off of the colors, whether sources have X-ray detections, radio detections, so detections in light other than optical and near-infrared, how interesting they might be. And we optimize this mask to try to get the most interesting targets possible. So that's our plan. And Ben is very good at this, and so we're setting up to look at all this maximally interesting mask. And so this process is fairly slow. We're about 90% complete on it. It takes about 5 minutes to put all the configurable slit units in place. I'll mention this is the same technology basically that the James Webb Space Telescope uses. It's something called a micro shutter array. It's basically just same sort of thing where, of course, you can't, haul a bunch of metal up to space, anytime you want to make a maximally interesting mask. So you have to have a little configurable unit inside of the telescope, side of the instrument, that allows you to send electronic signal and make movements to create your own mask. So like an instrument like Lemaux, which is another multi-object spectrograph on Keck, on the other Keck 2, that actually has metal that you mill, so it has to be laser milled, and of course you can't do that in
Lemaux,
space.
right? So
Yeah, like that. Yeah, that's what a Lemaux mask looks like. Yeah, so that is custom made, either in Santa Cruz or in Hawaii, and yeah, that you actually have to do laser milling for that. So that's not an efficient thing to do in space.
yeah, so basically what Brian showed, but so this is a different instrument. We are observing using different instrument, but one thing you can do is like wherever you have interesting targets. So I hope you can see tiny slits here. Maybe if I put light behind it.
Yeah, we can see pretty good.
Okay. Yeah, so see if I have light behind it, then it will come from the tiny slits, right? So that's a basic idea. But as Brian mentioned, right, like if I want to observe something else, I have to use a completely different mask. And you are not gonna like mill different masks and then ship them to space again and again whenever you want to observe things. So instead, what you can use is something like this.
No,
Is
we're
what-
there.
Oh, wait, did we reach?
Figuring, I'll go
Yay.
ahead and find alignment.
Okay, so this is the action part of the evening. So Ben just grabbed it. So we have this screen that we're looking at now. So on the left is a set of spectra that we took just for the previous target. So that's not what we're currently seeing. On the right is this slit mask alignment tool. And what this is going to allow us to do is make a very fine adjustment to the X, so the translational move, X and Y, and rotational axes for our slit mask to make sure that we have everything exactly where we want it within 0.1 arc seconds. So just to give you an idea, if you hold your arm out, a fingernail is about 1 degree. If you close one eye, fingernail is about 1 degree on the sky. An arc second is 1/3600th of that. And so 0.1 arc seconds is 36,000. Yeah. Yeah. So a very, very small, less than a hair's breadth on the sky. That's what the precision we're trying to do. And so we have in this mask, we have 5 what's called alignment stars, so that these configurable slit units make a box. And you'll see if we're in the right location, we'll see these stars show up in these boxes that say star 1, star 2, star 3, star 4, star 5. And the locations of those stars will let us know how to move the mask so that all of our less bright objects, so these stars are fairly bright, our less bright objects, we're sure that those that we can't see with a direct image like this are centered in our slits. So that's the basic idea. So again, because the sky is very bright, we have to take a sky frame, what's called a sky frame first. So the exposure complete that you just heard is our sky exposure. So we've just taken basically an image of blank sky. We have to do it at the same time as we take the image of the stars, because the brightness, both on a relative and absolute scale of the sky, changes very rapidly. And so this is going to be a subtraction of those two, and we're hoping to see the stars by the subtraction of the two. So let's see if we see them.
And we don't. I don't see.
And we don't. So Ben's now gonna take a look in our image to see if we see anything. I think you can bump the max up on that, Ben, if you can hear me. Or you probably know already. I don't see anything.
Yeah, let's see. Let's try another force alignment.
Yeah. Good.
Sending moves.
So you can probably just click no on all the X and Y and rotational values, and then just say send moves and retake image. That way you don't have to take a sky again.
Mhm.
Okay, so now we're fishing. We don't see our stars, so we're hoping we just did a course line, meaning so that was to get it right within like 1/3600th of a fingernail, and now we're going to the finer line, which is a factor of 10 more precise. So hopefully we got the stars in there.
Exposure complete.
Hmm. Is there some, well, can you stretch it a bit, Ben? I can't, it's hard for me to see if there's anything. Huh. What is it? Where are we right now? We are at
Not aligning well.
70.
Force alignment looks fine. Maybe we'll try a different. Maybe there's just not stars in the boxes at all.
Are they particularly faint, Ben? It doesn't look like it. They're 18. Do you want to bump up the exposure? Try bump the exposure. I just don't see any trace of them though.
Mhm.
Try 20 seconds.
I don't think there are any clouds. Yeah, no clouds. Your what's your brightest star, Ben? Like where on the mask is it?
Very
40.
15.1.
Yeah, it's TSU 40.
Exposure complete.
So Ben, if this doesn't work, do you want to move on to a different mask? Or what do you prefer? We could go to SWE.
Yeah, probably we could try doing a manual offset. There's been some times where that works.
Yeah. You could also open up the CSUs manually, right?
But we don't even have a hint of a star though.
Mm-hmm. Yeah. You can make the CSUs larger, but it would just have to be like that there was a translational offset.
In the PA? PA 56.
Yeah.
That should be correct, yeah.
Correct. Yeah, coordinates are fine.
Exposure complete. Not sure what else could be wrong. We could try a different guide star in case this one is.
The porcelain seems fine though, so I don't think it's. shouldn't be bad.
That would be an indication that perhaps the mass is not milled quite correctly.
Yeah, it's the CSU. So yeah, maybe it's.
The CSU.
Yeah, do you mind if I play around in the DS9 image just for a second?
Yeah.
That happened. Oh, it was not too long ago, but you're right. I just.
Yeah, no, I don't know. It's a good thought to be off in the info catalog.
Yeah, so slow.
Although it's the same one that was used to make the other masks. So should be okay. I think Brian's good to play around and yeah, if we don't see anything, we'll move to the mask.
My BNC is really slow. No, it's too slow to be worth it, but I think you're gonna have to play. I'm running too many things.
Okay.
If you bump it up, like, I don't know, if you can get dynamic range, like just bump it up to, I don't know, high of 14 or something, if you just see anything, because it looks like it's about 11,000 sky background in the boxes.
It's 14.
On the high end, yeah.
Yeah, I mean, it's pretty much the same all the way across the box. I don't think if there's something in there, it's getting really dispersed.
Yeah. Do the other SWE, does it have a better set of stars?
Yeah, there's two at 16, or there's one at 16 and a half, one at 17.2.
I go to that.
It's certainly brighter.
What do you think?
All right.
It's a bummer, yeah.
All right. Really, we're gonna switch targets. Highlighted SWE2 line 6. It's the tried to go to before. We lost guiding.
Okay. We'll still be above the elevation angle, and looks like we'll be at an okay physical driving angle when we get there.
Okay, great, thank you.
Well, that was weird. Okay, so we're gonna switch targets.
Mhm.
No, sorry, Ben.
Yeah, so now
Yeah,
we
I'm
are
just gonna say,
going
there's
to
a few times
SW2.
I've had it happen where sometimes automatically off it by a corner.
Yeah,
And so if we do like a manual move with the telescope, it can put the star into the box. But usually there'll be one corner will be a little bit brighter just from dispersed light than the rest of the box, and I don't even see that here.
agreed. Yeah. Yeah, usually it's off by, yeah, put it one corner or one side, but yeah. No hints, it's really hard to know where to move.
Right, Julie, we're okay to go ahead with the CSU?
Yeah. Looks like it should be good. My end.
Okay, well, we're gonna switch targets. We're gonna hope we have better luck with this next target. We didn't have any problems with the first two targets, and we're all in the same field, and so we're all in the same coordinate system. So something just funny happened with the mass that we were just looking at. So we're gonna hope we had pretty faint stars. We're moving to a target that has brighter stars to align on. Yeah, we're hoping that that's gonna help. So I think while we do this, Ekta, do you want to finish up what you were gonna share with everybody?
Yeah. Um, yeah, so I was gonna talk, oh yeah, really quickly, I found roughly how many resolution elements are in TNG. I think the one I showed had like this many elements, so it's like of the order of few billion resolution elements. So that's why it has like lots and lots of galaxies. So this is what I meant, like you can have really
This is
large,
the simulation, right?
yeah, this is simulations, and you can simulate smaller box with very large resolution or bigger box with relatively less resolution. But you can have, in the bigger box, you can find relatively rarer systems, like protoclusters. So it's you have to try out different things to see what works for the system that you are interested in. So we talked about like how you can use, how can you can represent like overdensity using some color. And then the red color can show like, denser environments, and then blue color can show relatively less denser environments. So so basically, and then if you look at different slices in redshift in the 3-dimensional space along the line of sight. So here is an example of that. And so pay attention to these parts, okay? And so we are basically at this point, we are going away from, if you are observer, if you keep going, looking at more and more distant redshift slice. So like take one slice at, let's say, 1,000 feet from here, and then take another slice as like 1,100 from here, kind of like that, but in much larger distance. So and then look at how the overdensity distribution change. So you can see that there are let me stop this again. So basically, as we go towards larger and larger distance, you can see that initially there was like the smaller region, but as we go larger and larger, it kind of gets bigger, right? These regions get even bigger. So these are very overdense regions. And then eventually it kind of fades away, okay? So if we look that in 3D, Where is it? Okay, so the example I showed was for this particular protostructures. So basically we were going from like here. Sorry, I think you guys just showed this thing. So I basically showed like this particular protostructure. So as you can imagine, like this is what the 3D distribution looks like. And here, instead of showing everything, I'm just showing like denser regions. So you can imagine like, we had like this kind of slices. So this axis is the redshift axis, or almost a measure of like distance along the line of sight. And this is like what you see on sky. So we basically had like slices in this redshift, and then if you combine all that, you get like this kind of connected structure. So here is an example of one of the structure, and you can see we have found many more of them. So I have just put a paper on archive, and our other group members also have discovered, they have also discovered protostructure. So Priti has also put her paper on archive, and Ben's protostructure, which is what we are observing right now, is he has already published a paper on this. So all of the structures, you can see they have very different shapes. But the basic idea is you can, if you use this kind of method, you can kind of actually see what is the 3D distribution of overdensities and how are different components of this protostructures are connected and all. Okay. Now, one of the challenges for this is to get like this
It might
kind
be
of
helpful, actually,
Yeah.
here to give just like an idea of the scale of these things. Like, first of all, like how distant they are, and then also like what are the kind of sizes that we're looking at? Are these like Milky Way sized, or are they smaller, bigger?
Yeah, that's a great question. So so these are actually redshift frequencies in very early universe. What is that in time? Is it 1.5-ish billion years?
1.5, yeah, I would say so. I can just do a quick calculation, but yeah, somewhere in that neighborhood.
Yeah, so it's like roughly 10% of current age.
Yeah, 1.8. So yeah, 10-15% of
10 to
current age of the universe.
15% of current age. So in very early universe, but they are very massive, very large. So I have shown like some scales here. So these are 4 megaparsec. I mean, 4 megaparsec is just like this size, but then the whole structure is much, much larger. And so it's much, so Milky Way, I think half-light radius of Milky Way is of the order of few kiloparsec, if I remember it right. So these are like much, much larger compared to Milky Way, and the mass of this is of the order of, like the total mass of individual system is of the order of more than 10 to the 14 solar mass. So it's like, more than billions of solar mass systems. So very, very massive systems in the early universe.
So this is hundreds and hundreds of Milky Ways mass wise. And I guess so, what is it, like half a megaparsec, 0.7 megaparsec, something like that, for the distance between the Milky Way and Andromeda. So I mean, these are huge scales we're talking about.
Mhm. Yeah, that's why these are giants in the early universe. So right now, so we are basically looking at this structure. So we are looking in the cosmos field, which we might have mentioned. So cosmos field is one of the 3 extragalactic fields that we are looking at as a part of C3VR survey. And here is the size of this survey. So it's a small area in sky, but it's still relatively large. So here is the size of moon, and this is the rough area on sky for this survey. And it has observed like millions of galaxies in more than 26 different bands. So 26 different types of like light. We will see more about like what do I mean by filter, but you can observe like green light, blue light, red light, and even beyond the visible spectrum. So this has each galaxy in this field has observations in lots and lots of different types of bands. So using lots and lots of different types of telescopes in space and on ground. So that will give you very detailed information about these galaxies. So this will be still color. And we want to look at even more detailed types of observations. So I will describe in a bit what I mean by the detailed type of observations. But yeah, so we are looking in this region. And as I said, so we are looking at the elementary structure that was in the bottom, the structure that Ben has discovered. And he has published paper on. So this is kind of like, if you take a slice on that and average out over relatively thin distance, but show the distribution. So the colors over here just represent different structures. So now it's not like, yeah, forget about like this color system for now, at least for this image. But the darker color here show denser regions, and then the lighter color show relatively less dense regions. And so as you can see, like this part is shown here, and then we have somewhat spread out structure here.
Exposure
Um,
complete.
and so this is also very, very massive.
Oh, thank God.
Did we do it?
We see stars. We see stars.
All right, send moves and retake.
Great. So
This is how it's supposed to look.
yeah. So if you remember last time, it was all like jaggy. But now you can see this very smooth light profile. So that's what they mean by we can look at stars now. So if you have stars, there we go.
This is what it's supposed to look like, you see? But you see the pointing precision isn't like super awesome. So the pointing precision can be RMS. You can end up basically just outside of the box. And so then what we could have done in the previous case is we could have just done slight movements in X direct in the 2X directions, take an image, slight movements in Y direction, just hope to land on it. But here we got lucky-ish and we landed on it. So.
All right, we'll try smooth retake once. Maybe just
I think we're good.
keep it there, I think, Brian.
I think you just send moves only and go for it. Yeah.
Okay. All right, Julie, if you please go ahead and mark the case there.
Okay, we're locked and loaded. We're ready.
Yay.
Time to do science again. Thank you, Preeti. Safe travels. Have fun.
Thank you. See you in the new year. Bye.
See you in the new year.
All of this I'm moving.
Ben, you're gonna attempt to put you're gonna go to the science mask?
I was not planning to, because it'll be the same for this one.
Okay.
Um,
Right. It's 2. Okay. Yep. Got it. Yeah. All right. Makes sense.
All right, and we are taking data.
Yes.
Oh, cool.
The other thing we could have done, Ben, which is the really annoying thing, is you make a empty. So you open up all the CSUs, you take an image, and then you take another image with the CSUs and location, and then you just match up the translational offset.
Yeah, I feel like that would take a bit of time though, right?
Totally. Yeah. That's like if you really wanted to get set on that mask, if you had like nothing else.
Yeah.
Okay. Since we are taking observations right now, let me really quickly show what we are observing. So Which mask is that? Let me
The Southwest E2.
Southwest E2. I think it is. I think it's one of these, right?
It's actually the furthest south mask.
Oh yeah, this one. Yeah. So I had shown Alentari, and so this whole region is actually even below this red part, because as some observations show that might be even overdense regions even below this already identified region. So we are targeting some of that. So currently we just switched to this mask. So basically we are trying to identify if there are overdensity of galaxies or lots of galaxies around the same redshift as Alentari. And if you see that, then maybe there could be part of structure over there as well that could be part of this large system. And then we also, these are the current targets that I don't know if we actually observed SWB, but I think we had targeted NIA. So yeah, and so one thing is, actually, let's see if the observation is done. Almost. So it's currently observing and 74% done. So basically it takes observations for about 204 seconds, which is what, little bit over 3.5 minutes, and collects all that light and put that in one image. Actually 3 minutes only, because the extra time is for reading and stuff. So each exposure is of 3 minutes.
Yeah, that's right.
Yay.
Exposure complete.
So this is the current image that we took. And we see lots of things. Don't stress out. We'll go a little bit into like, what does this mean? But yeah, it's live observations right now. Cool. We'll come back to that. Actually, I think Ben is checking something. Where is Ben?
Yeah, do you wanna explain next a bit what's going on in those in the image that we just saw? It looks like there's a lot going on there.
Yes. So that's what we were actually, that was the next part. So we are observing using the Spectrometer telescope. We'll see what we get. But basically, what you are looking at is if you take light, okay? So if you take light and if you we will come back to that. Let me start with a little bit more background. Okay, so basically you can.
Oh yeah, no, that's great. Yeah, do you wanna show that part? Yeah, that's great. And then we can come back to the. So actually, I Ben just told me that he has some reduced data from the first part of the evening. So yeah, maybe we could go. You could explain this, and then we could go to the raw data, and then we could go to the reduced data. Does that sound good?
Perfect. Yeah, yeah. So I'm really quickly gonna show even the telescope itself. So as I said, we have faint galaxies, and we wanna find out if they are at the same redshift or roughly at the same distance from us as this main structure. But how do we observe these faint galaxies in early universe? So we use really, really big telescope, right? So we use Keck telescope. Here is the mirror and you can see people. So this gives you some idea about how large the Keck mirror is. So basically it's a giant bucket and it collects all this light, and then and that's why if you're looking at faint system, but if you use really large mirror, then and focus all of that light into a single point, then you can really create sharp images of even faint object. And so there are two Keck telescopes. We are using Keck 1. This is a very small video showing like when it moves. I mean, at least you can see the scale. So you can see like there are multiple floors and stuff, and it's really big structure, you know, and this whole thing kind of moves as we are looking at different targets. So it's very magnificent. And so basically, you have this giant mirror, and then you have secondary mirror, and then everything kind of gets pointed here. And behind that is where your instruments usually lie. So you can have different instruments. We are particularly looking at MOSFIRE instrument, but I will say a little bit about that in a bit. So what we want to do is we want to use light to identify how far the galaxies are, right? And that whole process relies on the basic phenomena that we have seen around us. So we have seen like this kind of rainbows, or, you know, you have prism or this kind of glass artifacts, and you might have seen this kind of colors. And of course, you might have seen like series or something. So you might have seen like when you have white light, but when it has like bright source, it creates this like colorful patterns. And the same thing we can also see if you have something called grating. So it has like very thin lines of wires or other material, but basically if you have like very thin, very thin slit, it can create this diffraction pattern. So if you have like white source, in our case, this would be galaxies, and then you can have this kind of slit, which is what is provided by our MOSFIRE instrument. And then it passes through this grating, and then it creates this kind of dispersion of light. And what you can do is you can observe this light to then understand the galaxies and their properties. So as I said, we are particularly using the MOSFIRE instrument, which is shown here. So this is a human to scale. Here are some details about it. So this roughly the size is if you take like sixth part of the moon, it's roughly that kind of area of view. But you can observe like, you know, 20 to 40 galaxies as Brian mentioned earlier. So here is the basic what do you call it? Slitlets. I forgot the word. Is it slitlets?
Sorry, for which?
These things? Bars,
Sorry,
right?
my
Bars.
screen's lagging a little bit.
You have bars, and then these bars can create slits, right? I don't know why I'm blanking on word. But yeah, so basically you have this kind of metal bars.
Yeah. No, that's right. Yeah. These are just bars. Yep. Yeah, they're just bars that move. This is the part of the configurable slit unit. So they're just bars that move translationally in this dimension. So they can go anywhere. They can't move in Y or up and down vertically, but they can move along anywhere in the X dimension or horizontally.
Yeah, so you basically identify like where do your interesting galaxies lie, and then if your galaxy is here, then you want a slit there, right? So basically this bar, like imagine this whole bar can move this way and that way. So you can, in this whole entire view, you can have slits anywhere, right? It's kind of like it's like, you know, you can, if you want to observe my this eye, then I will have bars coming, and then two bars stopping like that. So you will just see the eye, right? It's kind of like that. So that's the basic idea. And using that, we observe these things. So now what are these things? So we saw this, right? Where you have grating, And so basically behind these bars, they have optical fiber, and eventually this light goes through grating and creates this kind of dispersed light for individual galaxies, okay? Now you can take different types of observations. So some of the observations are basically what we usually take pictures. It's similar to that. So imagine if I just measure all the red light, okay? So I will have like one value for the brightness in the red part, okay? And then if I have like one value for the entire light in the green part. So these are like typically what we call photometric observations. So in this case, you will only have like for this entire visible region, you will only have like 4 or 5 bands, okay? So that's one type of light. Another type of, but that's not sufficient. That can give you a rough idea about how far galaxies are, but it won't be precise enough. And if you want to look at galaxy clusters, then you really want to make sure that galaxies are actually closer to each other. So you need much more detailed information. So instead of that, actually what we do is we use spectrograph. So spectrograph is like if you look at even like smaller redshift region, it will have detailed information for like if you zoom in this region and how does the light distribution look. It's kind of like that. So here is an example. So again, so sorry, once again. So look at this. It's roughly 4,800 to 5,000, right? And here like 4,800 to 5,000. So imagine in this region, if you get like hundreds to thousands of observations, right? It's kind of like that. So how detailed you get will depend on your resolution, but the idea is if you zoom in, then you might be able to see this very sharp emission lines, and that will give you very detailed information about how far galaxies are, okay? So this whole axis, so these are three different observations, okay? So this is not one single system. So this axis is basically this axis, okay? So if you look at different colors or different, what we call different wavelength, then because these galaxies they can be star forming, and so they have like very specific kind of emission, and each element will have its own emission lines. And so we can find these emission lines, and sometimes these patterns are shifted. So imagine if this whole pattern, if the system is nearby, then this whole pattern would be a little bit on left. But if this whole pattern is shifted on right side or on the right side, then we measure like how much they are shifted from what we expect. And that will give you exactly, measure of how far the galaxies are. So this is the spectrum. So we actually, when we use these observations, we actually do see this kind of bright lines. So this kind of patterns, and that gives us information about how far the galaxies are. So this is what you see here. So since we have, lots and lots of slits, so for each of this slit, it gives you this information. So the x-axis is kind of like when you disperse through the prism, or in this case, diffraction grating, like at different wavelengths, what is the emission value. Now you might find it surprising, like why are there this kind of lines, okay? But even in our observations, we saw there are this kind of lines, right? White lines, white bright lines. So those lines aren't actually coming from our galaxy, because our galaxies are usually like, a small part of this whole slit, okay? So imagine like a dot that's slightly bigger than this pixel, but they don't span the entire slit, okay? So in other words, if something is spanning the entire slit, that means that observation isn't coming from our galaxy, because our galaxy is only small part. Here the vertical axis is like a spatial axis. So if you have slit, somewhere in the slit will be galaxy, okay? And things that are coming from galaxy, I think maybe you see this kind of horizontal line here. I don't know if that's real, but the emission that's coming from galaxy, you will see like a bright horizontal line. Right now, they have to be reduced. So we are mostly dominated by skylines. So these bright lines are actually emission lines that are coming from our own sky. Since we are on ground and not in space, we are really dominated by the skylines. And so they have to be removed, and then we look at the spectra of galaxies. So Ben will show reduced spectrum in a bit, but yeah, that's what we are looking at. Yeah, I hope that was useful. And as already said, what we are observing this part, and I'll be happy to answer more questions. That's all I had.
Thank you, Ekta.
Mhm.
That was great.
Any questions?
You said so this is just the raw data and it still needs to be reduced. Could you tell us a little bit about the reduction process or what we can expect this data to look like once it's been reduced?
I think feel free to chime in, Ben, if you wanna. I don't know if you're busy or if you wanna talk, feel free.
Oh, well, so Ben let me know where the reduced data are. So Ben did all the reduction and I downloaded the reduced data. So Ben's doing all the work. I'm just grabbing the data. Yeah, I can talk a bit about how you would go from a raw frame on the sky to the point at which it's scientifically useful. So calibrated data. So these exposures that we take are very short. They're 3 minutes apiece. And the types of objects that we're looking at are, let's see, somewhere around million to 10 million times fainter than can be seen with the human eye. So they're very, very faint. And I think my internet is unstable. Can you guys hear me still?
We can still hear you, yeah. Your screen
Maybe,
is
yes.
open, but we can hear you.
Okay.
Yes.
Okay. So yeah, so about 10 million times fainter than can be seen with the human eye. So 3 minutes of exposure, even with a super big aperture like the Keck 1 mirror, primary mirror, it's not going to do it. So you need to build up many exposures. And so we take many exposures, somewhere in the neighborhood of, I don't know, 20, 30, 40 exposures per slit mask. And we combine these all by doing these subtractions. So this difference, basically what's different, but basically amounts to difference imaging, but it's with spectra. So you subtract the first observation from the second observation from the third observation. It's a little bit more complicated than that, but that's the basic idea. And you get rid of these sky features. So the idea is to remove the sky features, remove the to remove the sky features completely, and then eventually to get a processed frame such that you can see the emission from the galaxies rather than the emission from the sky. So shall we see one? Let's see if I can bring it up. 1 second. Is this too hard to see with the full desktop?
It hasn't loaded on Zoom yet.
Nope, still. Yeah, internet is very slow. Let me try to.
Yeah, not loading yet.
Ekta, maybe you can try doing it. I can tell you where the files are in the box.
Okay.
I don't know what happened. The internet is, I guess I'm running way too many things right now, but my internet's super slow.
Yeah, I'm downloading it right now. Only one fits file, right?
Only one fits file, yeah.
Oh, plain
Jamaica, did you just disable screen sharing?
Oh, I reclaimed host, but you should still be, since you are having some intermittent connectivity issues, I thought I would take that off your plate, but you should still be able
Okay,
to.
thanks.
Absolutely. Let me make you a co-host again.
I'm not. Okay. Thanks.
Okay.
Ooh.
Mm. Scale parameters. What do we want? Let me actually do zoom. So this is what we have. Hmm. Let's see.
So it's just us now.
Hmm?
It's just us now. So we can go nice and
Oh yeah.
easy.
Oh yeah. Okay.
It was the exciting conclusion. We couldn't, technical difficulties prevented us from doing it. It looks pretty decent.
Mm-hmm.
Yeah, sorry, I'm not sure if it's lagging on my end, but I think you want to drop down the maximum quite a bit.
Yeah.
Yeah, you can see scale like that.
I think it is currently G-Scale though. Yeah, I already selected Z-Scale.
I think with the alignment star boxes, it makes the Z-scale not quite as effective.
Hmm.
So I'll tell you what I was using for scale parameters. I was using low of minus 0.18 and a high of 0.18, and it was coming through pretty clearly.
Okay.
And then just dragging, right clicking and dragging to change the color.
Oh, hold on.
We got a lot of emission lines there. It doesn't look like awesome, but it looks pretty decent. And a lot at the right redshift.
Exposure complete.
Yeah. So for example, if you see here, check out the box here. And if you see here, actually I can just zoom in. So you can see this line. This is kind of what I showed in my presentation, which is gone now forever.
I'm not seeing it. Maybe on my end, but I can't see it.
So kind of this is what we see here, right? You don't see it?
So no, I wasn't able to see it, but maybe that my computer's too slow.
Is it those
I
two?
can see
Yeah,
it, I can see it.
Yeah.
I see those. Okay.
Yeah, so this is an emission line. See how it's like a
There we
spot
go.
instead of spreading throughout the slit, because our galaxy is like isn't spread throughout the slit, it's only a point in the slit. So that's what we see. And then these things were the skylines, which are now subtracted. So that's why it kind of looks like that. So that's no longer like the brightest things, right? The brightest things are actual emission lines now. And then maybe there is something there. Maybe there is something there. So yeah,
Oh, there's definitely something there. Definitely something there.
and then maybe, yeah. Yeah. Oh,
It says
oh, I see,
it
yeah.
says the wavelength value there, right? So the wavelength value should be put it up. Hello?
Yeah.
So I think I'm lagging.
Yeah, I think I looked briefly, a few of them were slightly lower than the nominal lower bound, so about redshift 3.2 or so for a lot of these. But yeah, I think I counted 15 or so objects or something with an emission line.
This is good. So yeah, you already see a bunch of emission lines. Zoom out a bit. So basically, this is like 2-dimension, but then what you do is you kind of focus on actual region where you have emissions. So imagine if I just look at this spatial axis, right? So if I just say like, how do the emission changes as I go along the wavelength axis? So along this x-axis, so you can see like nothing, really bright thing, nothing, right? And that's kind of this kind of spectra, like nothing, bright line, nothing. And so we look at like these kind of actual light distribution, and then we see which lines are fitting, and using that, we get information about the galaxy. I guess it's just us though. Cool. Awesome data. I think this was, I don't remember a lot of shadow sessions where we were able to show this, so I'm happy about it.
Extra special for sure.
Show some results. That's always fun.
Thanks, Ben. Thanks for the hard work. And Bran, too.
Yes,
nothing.
definitely.
Just want to be clear here. I did nothing.
You suggested that.
Do we have time to at least in the last 20 minutes, whenever there's time, I'd love to get an intro from Emmett and Ben and also Brian.
Yeah, no, I can. Should I go? I can go first, or yeah. All right. So yeah, so my name is. Oh yeah, so I'm Emmett Marks. I'm a postdoc at Tsinghua University in Beijing. So it's like almost midnight here, as opposed to, Hawaii time, where and California and everybody else where it's like morning. Yeah, so I studied so when Ekta showed the plot of the morphology density relationship, that is one of the aspects of protoclusters that I'm been looking in. So basically, and galaxy clusters at low redshift, we're used to seeing them all having primarily elliptical galaxies, and them primarily being red. As you get to higher redshifts, it's relatively easy to look at color. It's much more difficult to look at the morphology, just because color, it doesn't matter how good or bad your resolution is, but for the morphology, if you have if your pixel size is very big, or so you're looking at a very large beam, you can't really see if something is kind of circular or if it's more elongated. But with high resolution, you can. So with telescopes like HST, so Hubble or James Webb, you can do this for really distant galaxies. So one of the things that I'm interested in looking at is kind of, when do galaxies in protoclusters look like galaxies in low redshift clusters, so in local universe galaxy clusters. And at what point does that happen? Because we know when it happens sort of with their color, but it's a little bit more vague as to when it happens with the morphology. because it's just much more difficult to do. So I'm interested in that, and also in galaxy-galaxy mergers within protoclusters and sort of the role that those mergers play in that buildup of the morphology. So I'm starting a project working on some of Ekta's protoclusters and looking at pair fractions, so galaxies that could be merging in those protoclusters as well. So yeah, so that is what I do. Yeah, and it's really a pleasure to be able to join everybody and join you all today.
Thank you so much, Emmett. That's really exciting. I would look forward to being able to follow up with you and your work, hopefully in 2024.
Yeah, definitely.
And Emmett, is this your first time observing on Keck?
This is my first time observing. Yeah, this is my first time observing on Keck. I was gonna say this is my first time observing not in Arizona. I think that's also true.
Really? Okay. The first time I'm on a Kea, then. Okay.
Yeah. Yeah.
Wow.
Yeah.
Awesome.
Exciting. Okay, next year let's do the other Keck too. And Subaru. All of them. Let's do all of them.
Simultaneously.
On a good night. Not on a bad day. It's not, yeah, let's not do that on a bad night.
Yeah. Yeah, okay, I can do a little intro. Yes, I'm Ben Forrest. I'm a postdoc at UC Davis. And yeah, I've had the good fortune to be observing this Keck for the last 5 years between UC Davis and UC Riverside. This is about like my 30-something night with Keck, which is very nice thing, and I feel very, very fortunate to have been able to do that. So yeah, I've been.
Oh, I
can't-
lost you.
Ben, I
Sorry.
think you got muted.
Yeah, it was me muting because Ben's talking through another computer.
Oh,
Does this work?
Would it be easier if I mute K1 and go directly on here?
Can you guys hear him now?
Yeah, we can hear him now.
Okay, yeah, no, it's okay. Sorry, that was me muting.
Yeah, no worries.
Too much technology.
So yeah, should I start from the beginning, or I don't know where?
yes, please start from the beginning, Ben. Thank you so much.
All right. Yeah, so I'm Ben Forrest. I'm a postdoc at UC Davis, and part of that is at UC Riverside. So I've had the great fortune to use Keck, and in particular MOSFIRE for like 30-something nights now, which is really, really cool. And it never gets dull. It's always exciting. So yeah, as people have been discussing, our group mainly studies protoclusters, so their formation and their evolution into the massive clusters of galaxies that we see in the local universe today, as well as analyzing how those environments affect the evolution of the number of galaxies. And so in particular, I'm interested in the most massive galaxies in these structures. How did they form? How did they end up growing these very, very large amounts of stellar mass, and eventually becoming what we call the brightest cluster galaxies, which are some of the most massive galaxies in the universe today. We think that their progenitors are these galaxies that would form in protoclusters at high redshifts, potentially growing their stellar mass not just through a lot of star formation in the galaxies themselves, but also through merging with large numbers of other galaxies in the system. And so that's kind of my main focus of study.
Exposure completely.
Confirm the existence of some of these things at very early times, and then model how they've grown their stellar mass, and whether they will continue to grow their stellar mass or if they will just evolve more passively, I guess. And so yeah, this has formed a nice synergy with the C3BO team as well, because the two areas of research, the protocluster evolution and then the evolution of massive galaxies, are very intertwined. So yeah, it's in a sense always fun to be observing, especially when there's good weather. So it's exciting to reduce the data, for those emission lines. It's fun. Yeah.
Thanks, Ben.
Thank you so much, Ben. And so you're controlling the telescope tonight, right? Is that my understanding? Right?
Somewhat, yeah. So there's always a team here at Keck that does part of that. But yeah, we generally make choices with the instruments. And then there's the professional at the Keck Observatory who actually moves the telescope. And we just have to control the instrument. But yeah, we're in charge of where we're pointing, what targets are we looking at, aligning the telescope, all those types of things.
Wonderful, wonderful. Thank you so much. And then this data that we were just looking at. So this is from earlier in the evening. Is that right? Yes, yes.
Yes, that was the first mask that we observed this evening, and yeah, I don't think we knew it at the time, but I think that was probably the best conditions that we're going to have through the night. But yeah, very pleased with how that data came out.
Thank you so much for being so wonderful as you were sharing things with us and keeping us up to date on things going on, Ben. It really is fantastic. And I'm really glad that we got to hear from you today because you've been so busy behind the scenes. I wanted to make sure that we highlighted you at least some portion of this session. Thank you so much. Brian, you brought us all together.
Is that true? I think astronomy brought us all together.
That's true. That's true.
Yeah, I'm happy to introduce myself. My name is Brian Lemaux. I'm a staff scientist at the Gemini-N Observatory. So this is an observatory that is on Mauna Kea. We have a twin in Serpachon in Chile. So just like Keck has a twin, we're on Keck 1 right now, and Keck 2 is right next door. Gemini North, which is just a couple hundred meters away from Keck on the eastern summit of Mauna Kea. So Keck is on the northern plateau of Mauna Kea. Our twin is not that close. It's many thousands of kilometers away, and so it can see the southern hemisphere as we can see the northern hemisphere. And so I have worked on Mauna Kea telescopes for 2 decades now. I think my first observing run was with Raja Guhathakurta in 2003 as an undergrad at UC Santa Cruz. And that was with Keck 2. And that was right when the Lemaux instrument, which is the other instrument that our group uses a lot, that was right when it first started on sky. So I think it started in, so that's what Ekta has there. That's the mask that Ekta showed earlier.
Yeah.
That's from Lemaux. And so I've been using Lemaux for almost its entire lifetime. And then MOSFIRE was like the new kid on the block, but that was 2011. So now more than a decade. But yeah, I do mostly massively multiplexed spectrographic science. So really deep imaging, and then following it up with a lot of spectroscopy. So these huge spectroscopic instruments that can target tens to hundreds of galaxies at a time. My first postdoc was in Marseille in the south of France. And this was working on a survey called VUDS, which is part of the name of C3VO. This was using the VMOS instrument on the VLT array, so 4 8-meter telescopes, also in Chile. And this particular instrument could target about 600 galaxies at a time to get spectroscopy. And so we could integrate for a very, very long time. We looked for galaxies that were about as distant as the galaxies we're looking at now, roughly. And we would integrate for about 24 hours. So so tonight we're just integrating for about an hour and a half. This was 24 hours of integration. So 12 on the red side and 12 on the blue side to get very deep spectroscopy in the ultraviolet, the rest frame ultraviolet of these galaxies, and to confirm their distances, and then to measure all sorts of fun properties of them. And so I did my thesis at UC Davis working on clusters of galaxies about halfway to the edge of the observable universe. And I got really interested in looking for the progenitors in this other survey, in this VDS survey. We happened to find quite a few of them. And this spawned about, now a 10-year investigation into what the heck these things are and trying to understand how to find them. I mean, to even figure out how to find them, it has been an extreme challenge. And not only myself, but the entire community that studies these sorts of structures have been grappling with how to find them for 2 decades now. And we're just now starting to like kind of get a little bit more mature in a way that we attempt to find these structures. And it's not like, hey, what's that? Hey, what's that? Cool. It's now we're starting to get a little bit more deliberate and make catalogs of these structures and be able to measure their masses and really start to hone in on what they look like and what kind of galaxies sit inside of them. But the C3VO survey is one of the forefront surveys in the world to look at these types of systems. We have incredible data, and we're getting more by the second right now. As I think Ekta mentioned, we have something like 400 candidate structures in the fields that we're looking at, and the one that we're looking at now is one of the more spectacular ones, but just this huge wealth of data. And so my expertise is really in density mapping, detecting these structures, characterizing these structures, and then so I'm the person who does a lot of the mapping, and then all these people do a wonderful job at looking at all the galaxies and how the galaxies form and evolve inside of them, and so that's our goal, and we're actually achieving that goal slowly but surely. And it's in large part to the having access to Mauna Kea. It's a wonderful observing site, and being able to use these just incredible telescopes that all of these incredible people work on and make possible for us. So that's the story here.
Yeah, and since we last talked, like in the meantime, my work, Ben's work, and Preeti's work, like we were able to do that work because of these observations, and all of us have submitted papers and all, so it's really happening in real time. And the shadow has been part of it because we had shown some of the observations. So yeah.
Yeah, the good parts and the bad parts. It's always an adventure.
Mm-hmm.
Yep.
Also, do we have observations? This is the last observations right now, right? We don't have any in spring, do we?
For now, yeah. So we're taking a break. I mean, we thought we were going to do a lot better this semester. I mean, we had 3.5 nights on Subaru, and we had 2 half nights on Keck, and we have a lot of data, and we have this giant HST campaign, which we're still in the middle of trying to figure out what the heck all these data are.
Mm-hmm.
And so we thought we'd just kind of catch our breath after what we thought was going to be a very nice observing semester, but with Subaru breaking their primary mirror, and yeah, only half night or not even quite that with Keck. Yeah, it's a bit sad. But we're going to come back with a vengeance, I think. Where I think we're going to have a lot of proposals coming up in the spring. And a lot of those are going to go on Subaru, I would guess, but still a decent amount of Keck stuff. And one of the things that I've been exploring more is trying to get stuff in queue, which is something we haven't talked about at all tonight, but getting some proposals into potentially Gemini, so that we don't have to worry so much about the weather, and even like we can average over things that happen with the telescope, because it's really disappointing. I mean, it's losing the nights it's devastating. And this is not, I mean, we're just in the thick of winter here, like every year, and we're losing 40 to 60% of the nights. And we've been doing C3VO observations now for 7 years.
Exposure complete.
7 years, and we're now like slowly staggering to the finish line. It's rough. And so I always was a proponent for classical observing, but when you don't get those nights, or something happens, or somebody is like it accidentally like a glycol leak happens during the day, I mean, then you can't observe, and then you have to convince the TAC again that your idea that you've already convinced them of, or other TACs, 10 times, is still a worthwhile idea just because weather happened the previous semester. It's a bit ridiculous.
Yeah.
So I talked to Ben and Lou about some proposals for Gemini, potentially, so that we can maybe go sleep a little bit easier. Sleep, first of all, because other people are taking the observations, or I will be taking those observations. And also that we can, the completion rate of proposals that are well ranked in Gemini, at least when we have a working telescope, is like 90%. I mean, it's pretty good.
Okay.
What we call band 1 proposals, those are, I mean, that's full depth, that's full time. I mean, almost all of them get at least a little bit of time.
Hmm. That could be good. I think then this might be then the potentially the last shadow where, like, at least I am officially a postdoc in this group, because my postdoc ends in September. I don't know if we have any observing coming up. So yeah. So thanks so much for the opportunity.
I mean, first of all, you're more than welcome to come to Gemini North sessions. And secondly, yeah, if we get some stuff in queue, then I mean, we can figure out what we can do about that. But I mean, there's a program called Priority Visitor Mode at Gemini, which is basically if your proposal is highly ranked, you can show up at the telescope as long as you can pay your way there. You can show up at the telescope and you just have to observe for a night. If the conditions are favorable for you, then you can observe your program. So your program is given priority. But then you have to observe everybody else's program afterwards. So it's kind of like, you get yours, but you also have to give back to the community. And so that's one way to actually have a almost coordinated shadow night in queue observing. So we're like classical adjacent sometimes.
Mm-hmm. Yeah, that would be awesome.
Who
We
knows what the future.
definitely, yeah, I was gonna say we definitely would look forward to any additional opportunities to follow up with you all in 2024 for sure, whether it's on Gemini, Subaru, or the amazing Keck Observatory.
Mm-hmm. I do want to show this random thing that I forgot to show. It's like diffraction of light, but through this weird thing. So Happy New Year with some lights, multi-valent light. And wish you all the best. Thanks so much.
Thank you so much, Ekta. Thank you so much, Ekta, Emmett, Ben, and Brian Lemaux. Oh gosh, we have one more person joining. Just a second. Oh gosh. We are.
It was this magic.
That's what it was. The pinwheel magic, Ekta, pinwheel magic. I love it. Oh, welcome, Christine. Welcome. We are actually just wrapping up a fantastic session here with Emmett, Ben, Ekta, and Brian Lemaux. Really quickly, I would open the floor to any of you to maybe share quickly with Christine what we looked at tonight, and maybe share one screen with her so she can maybe see some of the observations.
Sure. Yeah, maybe I can do that. Let's see if my internet's good enough for doing that.
Thank you.
Hi, Christine. Aloha. We are just finishing up, so the sun is just rising here on Mauna Kea in the Big Island of Hawaii. We're at, I think, just around 12-degree astronomical twilight right now. So the sun is 12 degrees below the horizon, so it's starting to get bright out here. And we'll probably stop observing, my guess is in about 15 minutes or so, and it'll become too bright for us to observe. We have been observing under reasonably cloudless skies some very distant galaxies, and we've been able to actually detect some and determine the distances to them. And so it's been a mostly successful observing night. We were observing on we're taking spectra of distant galaxies, and we're trying to determine their distance to determine if they were gravitationally associated with one another. It appears that at least in the first observations that we took, which are the ones that we've been able to process and get some analysis on, that indeed these galaxies are physically associated with one another. And so we will then take these data and spend the next, I don't know, 3 months, 4 months, 5 months trying to understand exactly what we see, and then eventually to publish a scientific paper on it. So that's the basic idea. I can share a screen. Let's see. Okay, so yeah, this is one of our screens that we use to control the instrument and the telescope. And so right now I'm Big Island of Hawaii, but I'm in Hilo, so I'm not on the summit of Mauna Kea. I'm interacting with Ben, who is helping to drive the telescope and the instrument. He's in New Jersey right now. We have our telescope operator who's in Waimea, which is in the middle part of the Big Island. And that is control. And then she's controlling the actual telescope, which is on the summit of Mauna Kea, which is about 20 miles away from Waimea. So we're all interconnected, but we're all using these VNC screens, these virtual screens to move instruments and telescopes around. And so this is one of the screens that we all look at. This is the part of the sky that we're looking at. That you can see on the left there. These are some stars. I can just change the contrast around a little bit, so we can see some of the stars. This is not actually what our instrument is seeing, but this is what the telescope is seeing, and it's tracking on one of these stars to make sure that we're pointing in the right location, and it's following the field across the sky as the field moves, and it's making sure that we stay in the precise location by tracking the star and making fine movements of the telescope. And so we're just moving with the sky right now, and our instrument is taking the light from the telescope, and we're getting spectra for a lot of distant galaxies. So that's basically what we're doing right now. We're just finishing up, just closing shop, and then we're going to take some calibration. So we're going to close up the telescope, and we're going to illuminate the dome, and that will help us to process these data, and then eventually to get science out of it.